Welcome to Lecture 5. In Lecture 5 we're going to think about continuous random variables, and the basic idea is that we're going to try and extend some of the ideas that we looked at in Lecture 4 with respect to discrete random variables. We're going to extend that to the continuous case. Remember that we were making this distinction between continuous and discrete random variables, and the idea of a discrete random variable was that there was a set number, a limited number of possible values that the variable could take. In the continuous case, we're going to move to thinking about a situation where there's an infinite number of possible outcomes, an infinite number of possible values that the variable can take. And if you think about what that means, then what that means is that any specific value has approximately a 0 probability of occurring. So any specific value of x occurs with probability 0, and instead what we're interested in is not the probability of a single value occurring, but the probability of a range of possible outcomes. So we're going to be focusing on ranges of outcomes. And maybe just to try and sort of fix that idea, really what we're saying is that suppose we're trying to measure something that we think of as a continuous random variable like height, the height of a group of students or something like that. What we're really saying here is that the probability of taking the height exactly, being of height 160 centimeters exactly, that probability is infinitesimally small. It's effectively 0. Why? Because we can always measure more accurately. We can always say, well, actually it's not 160, it's 160.01, or it's 160.001, or it's 160.00, whatever. So that's the idea. The idea is that we're measuring things continuously so that the probability of it being exactly equal to some particular value is very small indeed. And here's an example. A slightly different example. So we're going to define a continuous random variable x, which is the minutes spent in a queue, and this is going to be defined to take strictly positive values only. We can't list all the possible outcomes. There's an infinite number of possible outcomes for that kind of variable. And one way of thinking about it is that we can think about, even though it's not possible for any particular outcome to occur with a finite probability, we still want to make statements like some values of this variable are more likely than another. And we're going to introduce this idea that in some ranges, so this is the values of x going along the horizontal axis here, in some ranges of x we're more likely to find some ranges of x than we are others. In some areas the probability is more dense in some sense. We're going to use this idea of probability density, and in fact we're going to think about a mathematical function in a few slides time which is called a probability density function. And an analogy which is sometimes used is that the probability is distributed like paint on a wall. In some areas it's quite thick, in other areas it's not quite so thick, and so in the areas where it's thick, that's where we're more likely to expect to see values of x, in this case how long somebody queues up for something. So in this case here we're more likely to see values which are relatively low and less likely to see values which are extremely high. Okay, so we think that somehow the distribution of queuing times are more likely to be clustered around here than they are around here, but still the value of any particular queuing time, the probability of observing any particular queuing time is effectively 0. So that's just what that says there. So it says the probability of x being equal to any particular value c is equal to 0. We're going to concern ourselves with ranges. So we're going to be concerned with statements like the probability that x lies in an interval between a and b, two specific values a and b. And we can think about that in terms of the diagram that we looked at before as looking something like this. So here's a and here's b, and in fact what we're going to do more specifically is we're going to think about the area under the curve between a and b as representing the probability that the continuous random variable x lies between those two particular values. Okay, so that's going to be the idea that we're going to run with here to think about continuous probability. We're going to think about the area under this curve, this density function, as representing the relevant probability, in this case the probability that x lies between a and b. And if you're thinking ahead, or if you've read ahead, then you will appreciate that we often use the integral of a function in order to calculate the area under its curve. And in fact, that's exactly what we're going to do. We're going to think about that probability, the probability that x lies between these two values, as being the integral of this function here between a and b. And we'll come on and do that a bit more formally in a few slides' time, but we're going to get there. We're going to come at it from a slightly different angle, and what we're going to do is we're going to think about that integral directly, and we're going to think about what that function, if we think of that integral as being a function of x, what would that function look like? And we're going to call that function the cumulative distribution function, or CDF, and you'll see that there is a parallel here with what we did in the discrete case, where we also had a CDF. There are parallels between these two things, but there's also some important distinctions which we shall come on to in a minute or two. So we're going to define the CDF in a very similar way to how we defined it in terms of discrete probability, but we're going to use capital F to represent that CDF function, as opposed to capital B as we did in the discrete case. But the definition is going to be the same. It's going to be the probability that some continuous random variable x is less than or equal to the specific value x. So f of little x is the probability that some continuous random variable is less than or equal to that specific value, and that's going to be defined for all real values of x. Okay, so for example, big F of 2 is going to be the probability that x is less than or equal to 2. Right, the CDF has some properties. Like the discrete case, it's going to be bounded by 0 and 1. It can take the value 0, it can take the value 1, it can take all values in between, but it can't take values which lie outside the 0-1 interval. And unlike the discrete case, we're going to think about f of x as being smoothly increasing over ranges where possible values of x can occur. And just to sort of emphasize how that happens, we're going to think about f of 3, which is the probability that x is less than or equal to 3. We can think of that as being f of 2, the probability that x is less than or equal to 2, plus the probability that x lies between 2 and 3. Okay, so you can see that f of 3 is going to be f of 2 plus the probability that x lies between 2 and 3, which must mean that f of 3 is greater than or equal to f of 2. Furthermore, it must mean that f3 take away f2 is that remaining probability that x lies between 2 and 3. So let's look at some examples. We can always draw a picture of a cumulative distribution function. So here are some examples. This first example here, you can see that f is equal to 0 from -3 all the way up to 0 here. So the variable x never takes on values less than 0. And then we've got a CDF which goes smoothly up to 1 as x varies between 0 and 3. Okay, oops, what's happened there? Sorry. Let me get back to where we were. There we go. So yeah, so that's our first CDF. Our second CDF here, you can see this one is defined between -3 and +3, and it goes up smoothly from 0 all the way to 1 across that interval. The third CDF we're going to look at is defined between 0 and 2, and you can see that it increases linearly from 0 up to 1 between x values of 0 and 2. And if you wanted to, you could check that these are all valid cumulative distribution functions by checking that they satisfy these conditions up here. So you can see they all satisfy that they lie between 0 and 1 inclusive. You can see that they all satisfy this property that as long as b is bigger than a, f of b is greater than or equal to f of a. This third property we haven't mentioned now, but you can see that as x tends to negative infinity, then in the limit f of x goes to 0, and as x tends to plus infinity, in the limit f of x goes to 1. I think that's fairly clear from the diagrams. And finally, they all satisfy this property that the probability that x lies between a and b is equal to f of b, take away f of a. Okay, there are some important results, some of which we've met before. So for all random variables, that is for discrete and continuous random variables, the probability that x is greater than a is 1 minus the probability that x is less than or equal to a, or 1 minus f of a. However, for continuous random variables only, then the probability that x takes on the specific value a is 0, and the implication of that is that the probability that x is less than or equal to a is equal to the probability that x is less than a, because the probability that x is exactly equal to a is equal to 0, so that doesn't add any extra probability considering values of x which are equal to a. Okay, so that's the CDF, and what I'm going to come back to now is to think about the idea of probability density. Okay, and we said that the CDF, the cumulative distribution function, is the integral of a function or the area under a curve. And what we're going to think about now is, well, what curve is it the area under? Okay, so what function is it the integral of? And the function that it's the integral of is called the probability density function. Okay, so we're going to think about the probability density function. And this is a sort of formal definition of what the probability density function is, but intuitively it might be helpful to think about it as being the curve, the area under which gives us the CDF. So that's a good way of thinking about it. So let's think about this probability density function. And what we've got here is a continuous random variable x. So the probability that x is less than or equal to some value b, which we've called f of b, so that's the CDF up to b, or at the point b, in terms of the PDF is going to be defined as the integral between negative infinity and b of f of x with respect to x. Now f of x in this expression is the probability density function. So we're going to this statement here defines f of x as being the probability density function, and you can see what we're saying is that it's the function, the area under which gives us the CDF, this thing here, because we're taking the integral up to b of that function with respect to x. Similarly, the probability that x lies between a and b, we've already defined to be f of b minus f of a in terms of the CDFs. In terms of the PDF, that's just going to be the area under the curve between a and b, like we saw back in that diagram a few slides ago. So that's going to be the integral between a and b of f of x with respect to x. And given that, as it says in the top bullet point there, differentiation is the opposite of integration, effectively what we're saying there is that the PDF, little f of x, is the derivative of the CDF, big F of x, with respect to x. Okay, so in these we're sort of moving, integrating the PDF to get the CDF. Here we're explicitly saying that the PDF is the derivative of the CDF. And as I've suggested, it's the area under the PDF that gives us the probability that we're interested in. Okay, so there are some implications from what we've said of the properties of the PDF. So any PDF must satisfy the following things. F of x must be greater than or equal to 0 for all x, and for all possible values of x between negative infinity and plus infinity, the integral of f of x with respect to x is equal to 1. Now if you think about those, they look quite similar to the things that we looked at in the discrete case. In the discrete case we said that the probability mass function had to be greater than or equal to 0 for all values of x, and the sum across all possible values of x was equal to 1. In this case we're saying something very, very similar, but because we're talking about ranges of probabilities rather than discrete values of x, then we have to take integrals rather than doing the sums. Okay, here's an example. Here's a CDF. Okay, we're going to define a CDF as follows. For values of x less than 0, it takes the value 0. For values of x between 0 and 1, it takes the value x. And for values of x greater than 1, it takes the value 1. Now you can think about that in terms of what we looked at before, and you can see that it has the required properties of a cumulative distribution function. If we were to draw it, then it would look like that thing over there. What is the associated PDF? So if we think about this CDF, what does the PDF associated with that look like? Well, it looks like this. For values of x less than 0, it's equal to 0. For values of x between 0 and 1, it's equal to 1. For values of x greater than 1, it's equal to 0. Now, one thing that you will want to check is that, is this indeed the derivative of this? And you can see that it is, because if you think about differentiating 0 with respect to x, you get 0. You think about differentiating x with respect to x, sorry, I don't know what I've done there, let's get rid of that. If you think about differentiating x with respect to x, then you get 1. And if you think about differentiating 1 with respect to x, then you get 0, like so. So this function, little f of x, is very definitely the first derivative of the function big F of x, as we would expect. And we can draw that PDF as well, and if we do that, it's going to look like this diagram here. So it's 0 up to x equal to 0, it's 1 between 0 and 1, and then it's equal to 0 again for values of x greater than 1. Okay, so let's think about a specific example. Let's think about the probability that x is less than 0.25 or a quarter. Okay, so there's a quarter on the graph there. We're interested in the probability that x is less than a quarter. Now you can read that off directly from the bottom graph there. You can see that that's going to be the area of the red rectangle, and that's just 1/4 times 1, which is equal to a quarter. So the area there is going to be equal to a quarter. But you can also read it off from the cumulative distribution function, which tells you that big F of x is equal to a quarter. So that gives you the relationship between those two things. That shows you that the area under the curve of the PDF is just the value that the CDF gives you. Right. As in the discrete case, it's going to be very important to us to characterize the nature of the particular distribution that we're looking at. So if we've got, in the discrete case, a Bernoulli distribution, we might be interested in the mean and the variance of that distribution. If we've got a similar kind of distribution in a continuous case, if we've got some kind of distribution in a continuous case, we might be interested in the mean and the variance of that as well. And remember, again, we're talking in population terms here. We're talking about a model of probabilities. We're not talking about a particular sample of data in which we've got means and variances. We're talking about expectations. We're talking about characteristics of some model distribution that we are using to think about some kind of phenomenon in a statistical way. So here are the definitions. That's the definition of the expected value or population mean for a continuous random variable, and that's the definition for the variance. And you can see that they are analogous to the discrete case, except because we're using ranges of probability values, we're not taking sums, we're taking integrals. Okay, but otherwise they are quite similar. In particular, we can use this shorthand formula here for the variance of x, which which in fact is exactly the same. That formula there is exactly the same whether we're in the continuous case or the discrete case. Excuse me. Okay, let's finish this lecture with an example. So what I'm going to do is I'm going to put up a continuous random variable. There it is. That's a PDF, which says that f of x is equal to a sixth between 0 and 6, and it's equal to 0 everywhere else. So this is an example of a continuous PDF, a PDF for a continuous random variable, which has some positive probability of occurring between 0 and 6, but doesn't no other values of x actually occur. And there's the PDF there. Okay, now you can see just by drawing the PDF that it is a valid PDF in the sense that it integrates to 1. So the integral of f of x between 0 and 6 is equal to 1. In other words, the area of that rectangle is equal to 1. And you can see that because it's just 6 times a 6. It's a very simple example. Okay, so in that sense, this is a valid PDF. It's also a valid PDF because this is greater than 0, greater than or equal to 0 for all values of x. So it satisfies the criteria for a PDF. Now the expected value in this case turns out to be 3. It turns out to be the midpoint, and that is a particular feature of this kind of symmetric distribution. But we'll come back and we'll demonstrate that a bit more formally in a few minutes. And then on the last slide, we've got the variance calculation, which it's a few lines of algebra, but it's really just doing some fairly simple integration and figuring out what the actual outcome is. And again, I'll come back to that in a few minutes.